Section 1.2, Domain and Range. In this section, we are going to find the domain and range from ordered pairs, an equation, and a graph. We'll write a piecewise function to model a situation, and, given a piecewise function, we'll evaluate it for a given input value, find the domain and range of the function, and graph the function. So in this section, we learn how to find the domain and range of a function from three different representations. From a list of ordered pairs, from an equation, and from a graph. The easiest representation to work with to find domain and range are ordered pairs. For example, find the domain and range of this function, 0, 1, 2, 3, 4, 5, and 6, 7. So remember that the domain is a set of all the input values, or in other words, all of the x's. So the domain of this function, if we look at this set of ordered pairs and look at the x-coordinates, it would be 0, 2, 4, and 6, and we often write the domain as a set, meaning we put little squiggly brackets around it. Now the range is a set of all the outputs, or in other words, all of the y's. And so if we look at this set of ordered pairs that we have, the y-coordinates are 1, 3, 5, and 7, and so we would say the range of this function is a set 1, 3, 5, and 7. So domain and range from a set of ordered pairs, super easy. All right, let's try the next representation. To find the domain and range of a function written in equation form, you identify the input values, so that's the domain, and identify any restrictions on the input values and exclude them from the domain. And then you write the domain in interval notation if possible. So what functions have restrictions on their input values? Of all of the functions that were listed in the first section in our library of functions, the only functions that have restrictions on their input values are rational functions, rational functions are ones that look like fractions, and even root functions. For example, the square root, the fourth root, the sixth root. All right, so all other functions, the domain will be all real numbers. So for rational functions, what are the restrictions? So for rational functions, remember that we cannot divide by 0. And so when you have a rational function, the denominator, which is what you're dividing by, cannot equal 0. And we'll take a look at an example of rational function in a moment. For even root functions, the radicand, which is the expression under the radical sign, so this expression, whatever this expression is here, this cannot be negative. Because if we're confining our attention to real numbers, remember that you cannot take the square root or an even root of a negative number, because anytime you multiply a negative by a negative, you're going to get a positive answer. Okay, and we'll come up with an example of that in a moment too. Here, find the domain of f of x is equal to 2x minus 7. Is this a rational function? No. Is it an even root function? No. So the domain is all real numbers. Another example. Find the domain of x squared minus 3x minus 7. Is this a rational function? No. Is it an even root function? No. So the domain is all real numbers. Now there is a symbol for all real numbers, which you might see in your textbook. You can just write out all real numbers, but if you want it to be fancy, this symbol here that looks like a fancy R is sometimes used for all real numbers. So let's do some that are a little harder. Find the domain of f of x is equal to 5 divided by x minus 6. So notice that this is a rational function, and so we have to say the denominator cannot be equal to 0. And so in other words, we know that x minus 6 cannot equal 0. In other words, x cannot equal 6. So the domain is all real numbers except 6. Now we're often asked to write these in interval notation, meaning in symbols instead of as a phrase. So one way that is sometimes helpful to think about it is I often think about what the graph of all real numbers except 6 looks like. The graph of all real numbers except 6 would look like this. All the numbers to the left of 6, all the numbers to the right of 6, but just not 6. Sometimes a picture helps me write the interval notation because I can see it comes in two pieces. This piece on the left starts at negative infinity and goes up to 6, but doesn't include it. And the interval on the right starts at 6 and keeps going to infinity, but doesn't include 6. So a parentheses doesn't include the number, and a bracket includes. So we'll use the bracket if we have an equal sign, for example, in our symbol. So here we're not including 6, and so I've used parentheses in both places. And to show that the domain are these two pieces put together, we put this symbol in between them, and it's called a union symbol. It looks like the letter U, and it just means that the domain is the union or the uniting of those two pieces. Let's try another example. Find the domain of x squared minus x minus 12. Well, this domain is all real numbers because this is not a rational function and it's not an even root. Write the domain in interval notation. Well, the set of all real numbers is just the number line. The number line goes to negative infinity on the left, and it goes to positive infinity on the right. So this is what all real numbers looks like in interval notation. Now let's do an even root. Find the domain of r of x is equal to the square root of 3 minus x. So with even roots, we know that this radicand here cannot be negative. In other words, this radicand, the expression under the radical sign, must be greater than or equal to 0. It has to be positive, meaning greater than 0, or it can equal 0, but it cannot be negative. Now let's go ahead and solve this. So we'll subtract 3 from both sides, giving us negative x is greater or equal to negative 3. And here's something that we have to remember from our algebra. To solve this, we're either going to divide both sides by negative 1 or multiply both sides by negative 1, however you like to show your work. This is going to give us a value of positive x, but whenever you multiply both sides of an inequality by a negative sign, you have to take this negative inequality sign and reverse it. So you might remember that from algebra. And so our domain is x must be less than or equal to 3. So let's go ahead and graph that, and that'll help us write that in interval notation. All right, so here's 3. And we want the numbers which are less than or equal to 3. So equal to 3 means I include 3, and less than goes to the left. So in interval notation, looking at this graph, it starts at negative infinity, it goes to 3, and it includes 3. Now when we say this is the domain of the function, what that says is if I put in any value that falls to the left of 3, or even if I put in 3, then I can evaluate this square root. So for example, let's put in x is equal to 2. That will give us a square root of 3 minus 2, or in other words, a square root of 1, which I know is a real number and happens to be 1. But if I put in a number that's not in the domain, for example, let's try x is equal to 5. Notice it's not in the domain. If I were to plug this into the function, I would be looking at the square root of 3 minus 5, which is the square root of negative 2, which is not a real number. And that's why 5 is excluded from the domain of this function. Finally, let's find the domain and range from a graph. So the domain are all of the x variables, and the range are all of the y values in the graph. So here, if we look at the domain, looking at the graph horizontally from left to right, we can see it starts at negative 3, it ends at 1. I have an open circle at negative 3 and a closed circle at 1, and so that would be the domain of this function. For the range, I'm going to look in the vertical direction. So for the vertical direction, it starts at negative 4, it stops at 0, and at negative 4, notice I have a closed circle, and at 0, notice I have an open circle. And so this would be the range of that function. So when I'm looking at a graph, I think it's often helpful to draw in these arrows or these guidelines like I have in this one. The domain you're looking horizontally and the range you're looking vertically. Let's take a look at another example. Okay, we're going to find the domain and range of this graph. So the domain is the horizontal spread of the graph. So notice that it starts at negative 3 and it goes to 1. At negative 3, I see an open circle, so I'll use a parentheses. And at 1, I see a closed circle, so I'll use a bracket. And so this is the domain of that function. And now let's look at the range. Now the range is vertical. So vertically, I can see I start here at negative 4, and I end here at 0. At negative 4, I have a closed circle, and at 0, I have an open circle. And so this would be the range of that graph. One last example. Finding the domain and range. Again, domain horizontally. Now notice it starts at negative 4, but then this arrow indicates it keeps on going, meaning it goes to infinity. So the domain would be from negative 4 to infinity. And now let's do the same thing for the range. So for the range, remember we're looking vertically. We can see it starts at 0, but it keeps on going. And so this would be the range of that function.